students. In this video, let us find out magnetic force on current carrying wire placed in magnetic field under magnetic force on moving charges topic. Part 3. Already I said I will make 4 videos. In that the third video on magnetic force on moving charge. Right? My first video is about the equation and how we will find the direction of magnetic force. Second video, the circular path followed by the charged particle in magnetic field and finding its radius and time period equations. Now third, current carrying wire. Okay. Uniform magnetic field I took. Right. Uniform magnetic field. The direction will be direction of magnetic field will be into the page. Right? Right hand thumb rule here also. Middle finger indicates the direction of magnetic field into the field. Right? Into the field. Okay. I'm taking a straight wire. Okay. Some part is in magnetic field and some part is outside the magnetic field. So we are taking the explanation, we are confirming our explanation only up to this part of the wire which is lying in magnetic field. Let L be the length of that particular part of wire. B is the magnetic field. Now here first, current is 0. No current is flowing. Now, again I am drawing other diagram. Uniform magnetic field. Now, before current flows, wire is in such a way when current is 0, dotted lines. B is the magnetic field. Okay. Now, I will show what happens. Now, this is the wire. Okay. When there is no current, wire is in such a way. Current means what? Motion of electrons. Means motion of charged particles. Can I say? Negatively charged particles. Here motion of electrons. Current means nothing but motion of charged particles. Right? Now, this is the wire in such a way. Now, how is the magnetic force? Perpendicular, no? It is into the page. And in such a way, let us assume that in such a way the current is flowing in upward direction. Okay, in upward direction. Forefinger indicates the velocity or motion of charged particles. Middle finger into the paper, the magnetic field, and thumb represents the magnetic force. So our field is uniform field, no? Perpendicular to the motion of the charged particles. Now this perpendicular field shows its effect, or can I say it applies magnetic force on the wire? Yes. Wire or the charged particles in the wire. Now see how the wire is. It has moved or not? First, when current is not passing, there is no effect on charged particles when current is 0. So this is the position of wire. Now, when here current is, it is kept in the magnetic field. But there is no effect of magnetic field on this wire because there are no charge carriers moving in the wire. Okay, no charge carriers are moving in the wire when current is absent. So there is no magnetic effect on this wire. But when current starts flowing, current is flowing means what? charged particles are in motion. That we call it as current. The motion of charged particles we call it as current. Now, magnetic field, perpendicular magnetic field, it is showing its effect. Okay, it is showing its effect. So now see, the direction or the velocity is changed. Now let us draw this. Where is my pen? Here. How? In such a way, I am removing this. Hope you understood. Okay. Sorry. In such a way. Means what you understood? Magnetic force shows its effect on moving charged carriers only. Magnetic force shows or magnetic field shows its effect on moving charges only. First, they are stationary charges. It did not show any effect. Now here we are passing the current in such a direction, means here charges are in motion and magnetic field showed its effect on moving charge. Magnetic field showed its effect on moving charge. Understood the concept? Magnetic field showed its effects on moving charge. Here charges are not moving, here charges are moving. It showed its effect on moving charge. Now let us calculate the force. Okay. Let Q be charge. Single charge. Charge of single charge. So magnetic force on single charge. F equal to our formula QVB. In last two videos I explained, you see, no? QVB. Now let Q, capital Q be total charge. Number of charges are there, no? Total charge inside the magnetic field, can I say? Because wire is placed in magnetic field itself only, no? So now magnetic force on current carrying wire. Entire current carrying wire confined to this magnetic field only, not above, below, confined to this magnetic field. With length L, up to here length L you assume. F equal to, instead of small q, you keep total charge capital Q, VB. What is V? Velocity of charged particle. Velocity of charged particle. What is B? Magnetic field. What is Q? Total charge. Now, the time taken by the charge to cross the field. Time taken by charge to cross the field. What is time? Distance by speed or velocity, anything you say, no? That is distance L, it is traveling. Velocity V, we are assuming. From this we can write velocity is equal to L by T, no? Now substitute this velocity in this formula. Q L B by T. Or can I write this as Q by T L B? What is Q by T? Nothing but current. So F equal to I L B is the required equation. If angle theta is present in between I and B, this formula is written as I L B sin theta. Thank you.